All right, we're going to talk about empirical formulas now. This is kind of a continuation of percent composition, but make sure you have your note packet out. You turn to empirical formulas, you're ready to take notes. Again, you're always welcome to pause the video if you need a little bit more time to write something down, or even a little bit of time to just kind of think and comprehend about what's going on. I also recommend scrubbing backwards in the video just to go back and review the concepts that were just taught to make sure you really understand them. You can always go over them once, twice, 5 times, even 20 times to make sure you get it. Pausing the video also might give you a moment to talk with the instructor if you're not understanding something, to have him or her help you out, as well as to talk with each other. I encourage you to ask friends if they understand what's going on. The best learners are those who teach each other. So try to teach each other, try to learn from each other. Let's get started. So we're talking about empirical formulas. So empirical formulas are the smallest whole number ratio of the different atoms in a compound. So if we have a compound, here's some compounds, here's some molecular compounds. Here's H2O2, CH4, C2H4, and O3. Now, empirical formulas are the smallest whole number ratios of each. So here we have H2O2. The smallest whole number ratio of those two are just H and O, one of each. There's a ratio of 1 to 1. That's an empirical formula. How about CH4? Well, you can't really get any smaller than that. There's no smaller ratio than 1 to 4. So we have 1 C and 4 H's. How about C2H4? Same thing. It's a 2 to 4 ratio. So we can lower that to a smaller number ratio of 1 to 2. So C1H2. So those are our lowest whole number ratio. Now O3, it's the smallest it gets. We can't get smaller than that. So it's O3. I know for O3 it might seem like you can go down to the smallest whole number ratio of 1, but because this is a single element, it is at its smallest whole number ratio. There's no other ratio to compare it to. So those are empirical formulas. Now, why do we care so much about empirical formulas? Well, the truth is, a lot of times experimentally, if we didn't know what a compound was or we didn't know what the formula of something was, it's a lot easier to find the empirical formula of the compound than it is to find the molecular formula. I know that sounds weird, but if we had a substance in our hand, we might know the ratios, the smallest ratios of the atom, even if we didn't know what the molecular formula is of the atom. So we're going to kind of go that. So how do we determine the empirical formula of something? You have a long list here to tell you step by step what these are. I do want to add one to your list. This is not on your note sheet, so I want to recommend you to put this 0 here. The first step to determine the empirical formula of something is to determine the percent composition. Then we're going to follow through each of these steps. Now, instead of talking about these steps here, let's go ahead and use them in an actual practice problem. So here's the first practice problem. You can turn your page to find this practice problem. And we're going to go, and I'm going to leave the steps here. We're going to go step by step to figure them out. So let's do this. A compound contains 32.38% sodium, 22.65% sulfur, and 44.9% oxygen. Find the empirical formula. Well, again, this is exactly what might happen in a lab. We might be able to tell the percentages of each thing in the lab, but we need to figure out what the formula is. And we have to start with the empirical formula. So the first thing I said here is to determine the percent composition. This is not always given to you. However, in this formula it is. Notice that they are in percentage. That means that we have the percent composition. Sometimes we might be forced to find the percent composition, but in this problem we won't need to. So we found the percent composition here. They are the 32.38% sodium, 22.65% sulfur, and 44.9% oxygen. Now, part number 1 says turn percentages into grams. This is actually really easy. What scientists do is once they have their compound, to make it easier on themselves, they just grab exactly 100% of this compound. And if they grab 100% of this, 100 grams of this compound, if they grab 100 grams of this compound, then by default, 32.38% of that must be sodium. On top of that, 22.65% of that must be sulfur. So if we have 100 grams of the compound, then really easily 32.38 grams of that must be sodium, 22.65 of that must be sulfur, and 44.9 of that must be oxygen. So it's kind of a trick. It's kind of a useful trick that scientists do. We take 100 grams of our compound. If we know the percentages, we can just convert them directly into grams. So that's what we do for the first, turn percentages into grams. Next, it says convert grams to moles. moles. This is where we use our molar conversions, and what I'm going to use is the molar mass of each substance. So if I take 32.38 grams of sodium and I multiply that by 1 over the molar mass of sodium, this is found on the periodic table, I get the number of moles of sodium. Same thing, I'm going to do that with sulfur, times it by 1 over 32.07. So in essence, I'm dividing it by the molar mass, but anyways, I'm timesing it by 1 divided by the molar mass. That gives me 0.7063 moles of sulfur. Finally, oxygen, I'm going to do the same thing, and I'm going to get 2.806 moles of oxygen. So that's part 2. Part 3 says determine the element with the fewest number of moles. Well, that's the second one. That's sulfur. Sulfur has the fewest number of moles. So 4 says divide each element's number of moles by the smallest number of moles in step 3. So if this is my smallest number of moles, I'm going to take all of these moles and divide it by the smallest number of moles. Done. Now I'm going to go ahead and calculate this out. These last two parts right here, 5 and 6, are kind of one step in themselves, but if I go ahead and multiply this out, the first one I'm probably going to get something like 1.99. So if it's 0.1, round down. If it's 0.9, round up. So I'm going to round that up to 2. The next one is perfect. It's a 1-to-1, so it's just a 1 ratio. The last one, I think I got 3.99, so I'm going to round that up to 4. So again, if it's 0.1, round up, or round down. If it's 0.9, round up. If it's 0.5, multiply. We didn't really see step 5. We'll see this next time, so don't worry about step 5. So what do I use these for? What's the point of these numbers here? Well, this helps us with our empirical formula. I'm going to take sodium, sulfur, and oxygen right next to each other, and then I'm going to use these ratios here to write them in. So my formula is actually Na2S1O4, but remember, we never write ones for a compound, so I'm going to delete that 1, and it's just Na2SO4, which is basically sodium sulfate, which is kind of cool. So that's an empirical formula right there. So try this one on your own. See if you can figure this one out. Pause the video. I implore you to see if you can figure this one out without my help first, and then I'll help you to see if you got it right. Did you pause the video? I sure hope you did. Let's go ahead and check your work. Okay, the first step, step 0, says to determine the percent composition. Now, we don't need to do that. It's already written here, but sometimes we might. We might be given problems where we have to take whatever grams of something we have and determine the percentages of those grams. But in this instance, we won't. So 43.7% phosphorus, 56.3% of oxygen. That is our percent composition. Step number 1 says turn percentages directly into grams. So I'm going to skim off 100 grams of my unknown substance, and I'm going to just be able to convert those directly into grams. So I have 43.7 grams of phosphorus, and I have 56.3 grams of oxygen in my 100 gram sample, which is totally cool. I love that we can do that. Next, convert grams to moles. So I'm going to use the molar mass to convert the grams of each into moles. So here's my molar mass of phosphorus. Here's my molar mass of oxygen. I'm in essence taking 43.7, timesing it by 1, and dividing it by the molar mass. And then I'm taking 56.3 grams of oxygen, timesing it by 1, and dividing it by the molar mass. And that gives me moles of each substance. Next, it says determine the element with the fewest number of moles. Well, in this case, it's phosphorus. Phosphorus has the fewest number of moles. So step 4 says take each element's number of moles and divide it by the smallest number of moles in step 3. So I'm going to take each of these and divide it by phosphorus's moles right there. That's going to give me a ratio. Now, when I calculate that out, the first one up here is equal to 1, and the second one down here is equal to 2.5. So this is where step 5 and 6 come into play. In this instance, I've gotten about a 0.5. So it says here, if I get a 0.5, multiply that so I get a whole number here. Well, what's the best number to multiply things by? Well, 2. And I can't just do it with this one. I have to do it with both. So I'm going to multiply both of these by 2. So up here, my phosphorus ratio was 1. I'm going to multiply it by 2. That gives me 2. My oxygen ratio is 2.5. I'm going to multiply that by 2. I'm going to get 5. So my ratio here is 2 phosphorus and 5 oxygen. This is a covalent compound, diphosphorus pentoxide, and this is my empirical formula. All right, guys, I think that's about it for empirical formulas. Please try the practice problems. Again, you can always go back, rewind this video, listen to some things again, make sure you try to understand. I encourage you to talk with each other, to teach each other. The best teachers, the best learners are those that teach, and hopefully that's you guys. You can also learn from your instructor. He or she should be walking around the room to help you out, but good luck.